This one is meant to trick you a little bit. It makes you think about what's going on in this circuit. Notice that as the circuit is set up, we've got X sub L to the far left of the source, and we've placed the load resistor then between R. Now remember from your fundamentals here that it doesn't matter which side that R and RL is on. When you remove RL from the circuit, you still have R. So in this one they ask us to find the Thèvenin for the circuit within the box as viewed again between A and B. So first we remove the load resistor, R sub L, and determine the voltage across the resulting open terminals, which is Thèvenin. Find Thèvenin by applying the voltage divider formula to X sub C and R. And you'll notice X sub C, our capacitor, is already in its reactive terms. So Thèvenin then is equal to the voltage across the resistor R. So R at angle of 0, R minus J X sub C because it's a capacitor, times V sub S for the source. So when we do that, again, we've got the rectangular terms in the denominator, we've got our polar terms in the numerator. So you're going to convert 10k ohms minus J 10k ohms into a polar form and divide that then into the 10 multiplied by 5. So when we do that, we get 14.1 at an angle of minus 45 k ohms that we're going to divide into 10 at 0 degrees k ohms. So multiply it times 5. So when we do, we have 3.55 at an angle of 45 degrees in voltage. Notice that X sub L has no effect on the result since the 5-volt source appears across X sub C and R in combination. Okay, so a little bit of a tricky one here for you. In the previous examples, we concentrated on looking at and finding Thèvenin. Now let's determine the Thèvenin equivalent impedance for these circuits. The second part of the Thèvenin equivalent circuit, as defined by Thèvenin's theorem, Thèvenin's equivalent impedance is the total impedance appearing between two specified terminals in a given circuit with all sources replaced by their internal impedances. So to find Thèvenin between two terminals in a circuit, we replace all the voltage sources by a short. Any internal impedance remains in series. Replace all the current sources by an open. Any internal impedance remains in parallel. Then determine the total impedance between the two terminals. The following three examples then illustrate how to do that. Okay, so in the previous 6 examples, we were shown how to find two equivalent components for a Thèvenin circuit, Thèvenin, Thèvenin. Keep in mind that we can find Thèvenin and Thèvenin for any circuit. So to find Thèvenin for the part of the circuit that's within the beige box, we look at across again, looking in terminals A and B. This is the same circuit as the previous example, 19.4. So first replace V source with its internal impedance, 0 in this case. Looking in between the terminals A and B, R1 and X sub L are in parallel. Okay, thus Thèvenin then is equal to R1 at an angle of 0, X sub L at an angle of 90, our polar terms, and then R1 JX sub L in the denominator. So we end up with polar in the numerator, rectangular in the denominator. We do our conversion to polar in the denominator. We get 112 at an angle of 26.6 ohms. Now we can combine the terms in the numerator, 50 and 100, divide that by 112, and then we have 90 and 26.6. When we take the difference, then we get 63.4 degrees. So 44.6 at an angle of 63.4 degrees in ohms. So now we have then a equivalent circuit here of R1, how we calculated this R1, X sub L, V source zeroed out. Okay, now we're going to again take a look at the circuit we've already seen. In this case, we're going to determine Z Thevenin for the circuit within the box. First, replace the voltage source with its internal impedance, 0 in this case, as shown in the figure. So there we are, V source is zeroed out. We remove our load resistor. We're left with R2 and X sub C1, X sub C2, and R1. Looking from terminals A and B, C2 appears in parallel with the series combination R1 and C1 because now we've closed this point. So we've got R1 really connected right here at the ground side of C2. This entire combination then is in series with R2 over here on the output side. The calculation for Z Thevenin then is, okay, again, we are going to take Z Thevenin, let it equal to R2 at 0 because that's our pure resistor, and then our product over the sum. Again, phasorially speaking, we go through our conversions and we end up with 3.16 at an angle of minus 71.6 degrees in k ohms. That we divide into the numerator once we combine the terms here, and we end up with then one more time we would have to do a conversion because we're summing polars and polars. This gives us 560 ohms. Okay, that stays just as is, and our polar form here then becomes 225 minus J824 when we do our conversion. Now we can combine our terms, real and imaginary. 785 minus J824, do our polar conversion, 1138 at an angle of minus 46.4 ohms. If we look at this one, again, we want to determine Z Thevenin for the portion of the circuit within the box. Same circuit as example 19.6. Again, we go through the same operation here. In this case, we're going to remove the source and replace it with a short. So V short circuit here then, and we're going to open up the load. So by doing that, V Thevenin then is equal to the product over the sum. We end up with 7.07 at an angle of minus 45 k ohms. So again, the easiest and best way to learn this is go through, pull out your calculator, run through each of these steps, do the conversions so that you are used to it. Hopefully your calculator is one that has the conversions in it to make this process simpler for you. Okay, so when we come back then we'll take a look at these examples just for a quick practice.